And I want to dedicate this talk to a good colleague and friend of mine who passed away a couple years ago, Doug Engelbart. Doug Engelbart was the inventor of the mouse, and he was also the inventor of what's called augmentation theory. And this augmentation theory is about how people and organizations are going to leverage technology to augment their capabilities. So think of your capabilities today, and then think of them augmented with this amazing technology that's coming. And that's what Doug, he's also famous for the mother of all demos. So today's talk, I'd like you to start thinking about two questions. What should we know how to make? All right? Do you know how to make your breakfast in the morning? Of course you do. But what should we know how to make? And what might programming education become? And what I'd like you to think about is building blocks. Because what we can make depends on the building blocks we have. If we have better building blocks, we can make better things. If we don't have such good building blocks, you know, if you've got rocks as building blocks, you can only build certain things. But if you've got very, very powerful building blocks, what you're going to be able to build is amazing. And the next generation of computer scientists are going to have the most amazing building blocks in history. And I don't know how many of you are fans of Lego, but when I started Lego, you just got the blocks. But now you can get these amazing kits, mindstorms, robotics, and so forth. So it just shows, again, this concept of if society provides the next generation with the right building blocks, you'll be able to build amazing things. So in today's talk, I'd like to first begin by giving a brief history of knowledge and making. And there's this wonderful presentation. It's online. There's a video from a person at the MIT Media Lab where he talks about person byte and people byte. Because when you think about knowing things and making things, there's what can an individual person know and make, and then what can a company like IBM know and make. And obviously, if you're thinking about IBM and the 360,000 people that work at IBM can make much, much bigger things than an individual. And this talk from MIT does talk, though, about, if you think about the amount of knowledge that was in the world in the days of our ancestors, in the days of early people, the amount of knowledge that our species had wasn't very much bigger than the amount of knowledge you could have in one head. So making a fire was high tech in the early days, and that's knowledge that could fit in one person's head. But a little later, as time progressed, and you start thinking about some of the early cities and some of the beautiful European cities, the amount of knowledge was much more than an individual person could have in their head. There was a lot of knowledge required to build cities. And then in the industrial era, if you think about the dawn of the industrial age and making of various types of clothing and chemicals and a lot of the early products, here the knowledge again was much, much larger, and you're starting to get into what's called the people byte era. And here we are today in a network global economy where the amount of knowledge that our people have is just increasing at exponential rates. So there's more and more knowledge, certainly more than can fit in an individual person's head. What can one person know and make? There's a wonderful book, I don't know if any of you have ever heard of it, it's called iPencil. But even something as simple as a pencil contains more knowledge than a single person can fit in their head. I mean, it's just incredible if you think about the eraser and the chemicals, that little metal strap that holds the eraser on, the paint that goes into it, the type of wood, the graphite, there's just a huge amount of knowledge that's been accumulated over the years and is in different specialized groups to make something as simple as a pencil. I love this, this toaster project. This was one student decided he was going to try to learn as much as he could to make one thing, and he wanted a simple thing. So he went out and bought, I think, a toaster that cost about $3, and the picture of the book shows the toaster that he was able to build. He had to learn how to make plastic, metal, all of this knowledge he had to acquire in order to try to build a toaster. And it's a wonderful video. He also did a TED Talk. But my point is simply that if you don't have the right building blocks, it's very, very hard to build complex things. But we're going to enter an era in the next 20 to 40 years where we will have the right building blocks, and individuals will actually be able to build things of tremendous scale. Organizations and groups of people will be able to build even bigger things. So we have to start expanding our imagination about what we want to build. There is this thing called the maker movement. There's a wonderful book out called The Maker Movement Manifesto by Mark Hatch. I've met him. He's the CEO of Tech Shop. There's a few tech shops around here in Silicon Valley, and you can go in there and you can get 3D printers and you can get all kinds of amazing tools for building things. There's also a project called the Open Source Ecology, where a group is looking at the 40 most important industrial machines, and they're building processes and kits. So you can take the knowledge for these machines, it can fit in an individual person's head, and they can try to build these. So once again, both the Maker Movement Manifesto and the Open Source Ecology is really doing a good job of rethinking what are the building blocks for making things. Now obviously these are physical things, not just software, but we're going to get to that in a minute. What does this have to do with programming and computation? I'm sure you've all heard of Alan Turing and John von Neumann, very famous figures in mathematics and the early days of computer science. And both of them had a passion for thinking about, in fact, they dreamed about universal machines and constructors. So the idea here is they were thinking about, what if you could build one machine? You had the building blocks to build one kind of machine, but that machine could build all other machines. It could build itself. It would be self-replicating. Think about what that does to knowledge. All the living things we see around us, people, animals, plants, are built from DNA. So there's a fundamental building block that allows all of this diversity of life. What if, what if we could figure out what is the right building blocks to build all the physical stuff as well as life? So anyway, this is the question that I find very interesting, because if you can figure out how to build a machine that can build all other machines, in some sense, you've found the right building block. So computing continues to progress. And in the early days of computing, computers were people. In fact, they were mostly women. And they were actually called computers. And they would sit in rows at desks, and they would compute, typically adding numbers or moving papers and shuffling things around. And there was an organization to their movements. They would work on big processes, and papers would have to move from one position to another. But this was the early days of computing before we had machines to do the computing, complex computing. In the background, you see a chart. It's a pretty famous chart by Kurzweil that shows the exponential growth, and each dot is what $1,000 will buy in terms of computing. And what's fascinating, if you look at that graph, is what you see over there on the logarithmic plot, that we're kind of at the level of an insect or a mouse in computing power, what $1,000 of computing will buy. But look out 20 years, and you see the curve crosses one human brain. And look out 40 years, and you see the curve crosses not just one human brain, but tens of billions of human brain, all human brains. So when I say this is an exciting time to be a computer scientist, when I say this is an exciting time to be a student of computer science, when I say it's an exciting time to be a researcher in computer science, like I was back in Yale in the 1980s, it's even more exciting today. During your careers, if you're a computer science student, during your careers, you're going to see, if Moore's law continues, you're going to see computation that is at a scale that's much, much larger than certainly I could have imagined when I was writing my first program on punch cards. So let's explore the implications of this in terms of what the building blocks will be for making things. So when I grew up in Maine, in my house in the 1950s, that was a picture of the phone that was on the wall. It had a crank, and it was called a party line. And by 1975, I was at MIT studying physics, and that was the phone in my dorm room. It had a rotary dial. In 1995, I was here in Silicon Valley, and I had my first mobile phone when I got here in Silicon Valley. And 2015 today, you know, you see these kind of smartphones. But what will it be like in 2035 and 2055 if Moore's law continues? By 2035, my phone will, for $1,000, will have the ability of a human brain. And by 2055, my phone will have the ability of the entire population. So what does that mean? Well, one thing I should mention before I get into what that means is I found this as I was researching this talk. I found this slide kind of interesting. There's a quote by Einstein that says, "I fear the day that technology will surpass our human interaction. The world will have a generation of idiots." And you can see here there's little pictures of having coffee with friends and everybody staring at their phones. A day at the beach, everybody staring at their phones. Cheering your team, staring at the phones. On an intimate date, staring at your phone. Enjoying the sights, driving around in a beautiful place like California, looking at the sights, staring at your phone, and having dinner, staring at your phone. And this is definitely a concern. As we get more and more powerful technologies, life could become easier, and if we're not careful, we could end up in the world that Einstein worried about, this generation of idiots. But I don't think so. I think it's a very competitive world out there, and as we get more and more powerful technologies to help us, we're actually going to be able to start dreaming bigger and doing even bigger things. So what exists today? So if you look in 2015, you've probably all heard about Watson, IBM's Watson, and winning in Jeopardy in 2011. About 2 decades ago, of course, IBM built the Murray Campbell, helped IBM construct the first computer that was able to win in chess. And in 2011, a team in IBM Research built the first computer that could defeat champions in the game show Jeopardy, which is a quiz show where you have to have all of human knowledge. Apple, of course, has Siri. Microsoft has Cortana. Google has Google Now. And Amazon has come out with a new product called Echo. And all of these are intelligent systems, cognitive systems. In fact, if you go to Wikipedia and you look up intelligent personal assistant, I do this about once a month. About every time I go there, there's a new company added to the list that's working on intelligent personal assistants. So in 2015, we're starting to see a lot of intelligent personal assistants. By 2035, these intelligent personal assistants will have the power of a human brain, and by 2055, these intelligent personal assistants will have the capacity of the entire population if Moore's law continues. So we're starting to see cognitive assistance for all occupations. IBM alone, we've come out with cognitive assistants to help doctors and medical professionals. We've come out with cognitive assistants that actually help chefs, the creators of different recipes at Bon Appetit magazine. Many, many different areas, including computational biochemistry and other areas. In fact, as part of my roles at IBM, I not only lead our university programs worldwide, but I also lead our Cognitive Systems Institute, which has the mission of working with computer scientists and cognitive scientists and all different disciplines to develop cognitive assistance for all occupations. And in the U.S., we have a website called ONET Online, which stands for the Occupation Network. It's a list of 1,000 occupations. So everything from accountant to zoologist. If you look at this slide, you can see some of the ones in between. And you can see they fall into different job families, like business and financial operations, or production management, arts, design. There's a lot of different job families that these jobs fall into. There's over 1,000 occupations here. And they're all getting cognitive assistance. That's the point. Let's zoom in on one, biochemical engineers. So if you go to ONET and you click on biochemical engineers, you see this information. And what it does is for every occupation in ONET, they break it down into the types of things that you have to do to perform that job, to do that occupation. And it's probably too small for you to read, but the second item on the task list here for biochemical engineers, I'll just read it to you. It says, read current scientific or trade literature to stay abreast of scientific, industrial, or technological advances. How many papers a day do you think are published in biochemistry? Hundreds? Thousands? How many in German? How many in Japanese? How many in Korean? How many in all these languages? There's no way anyone can possibly keep up with the thousands of papers coming out in biochemistry without cognitive assistance. So at the Almaden Research Center, the researchers worked with a particular biochemist who was at Baylor University, and this group of biochemists were trying to discover molecules to fight cancer. They are a group of about 10 researchers, and their productivity was they would come up with about one new interesting molecule per year. But this group, there was a particular, they had identified 60,000 research papers that they wished they could read because in those papers they were sure there were molecules that were relevant to their research. And IBM, and by the way, 60,000 papers, there's no way this group of 10 researchers could read that number of papers in their lifetime, really. It's just too many. But working with IBM Research, they developed a cognitive system that was able to ingest those 60,000 papers in just a matter of minutes. And this system, which knew about their research and their publications, acted as a cognitive assistant and said, you know what, out of these 60,000, here's the ones you really want to read because they're the most relevant to the future discoveries that are of interest to you. And within 3 months, they had discovered 10 new molecules. So a dramatic increase in creativity and productivity measures for this group. And this is what's coming to all occupations, not just biochemistry. Who can keep up with the emails coming in? Who can keep up with their research area, especially with China coming online? If you think of all the different languages that discoveries are coming in, it's physically impossible for any person to keep up with all this information. So we're going to need to have these cognitive assistants. And I think by about 2035, we'll almost be symbiotic with our cognitive assistants. And here's another thing. How well do you know yourself? Your cognitive assistant, how many of you can remember emails that you sent to people 2 years ago? your cognitive assistant will be able to do that. So your cognitive assistant will have a model of you. It'll know you. It'll know how to engage you. It'll know how to empower you. So we really are heading into this era where we'll have cognitive assistance for all occupations. And I believe in 2035, people will look back and say, just like kids today with smartphones, how did they live before they had smartphones? How did they, sync up and locate each other? People will look back and say, how could we have lived without these cognitive assistants? So here's a little brief history of artificial intelligence. By the way, I was born in the middle 50s, and so this is sort of, I know these things very well because in the 80s, I was a computer science PhD, actually studying how students learn programming as part of my research at Yale, and how to build intelligent tutoring systems and models of students learning programming. And here we are today with the Watson capability, and we're starting to move into an era of cognition as a service. And this is really where I'm going to get back to my point about the building blocks, and these building blocks in the cloud. And I do have a quote here where I say, up until now we've been using cognitive shovels, but these new tools are like cognitive bulldozers, and we're all going to be having these very shortly for all occupations. But there is a difference between our brains and computers, right? In fact, a lot of people look at that Moore's Law curve and they say, it's not going to happen. It's going to stop. And usually the reason they say it's going to stop is energy. If you look at your brain, in fact, if you touch your head right now, you don't burn your hand. In fact, my head feels cold, even though I'm standing up here giving a talk and apparently working hard, but my brain, or my head feels cold to me right now. Good air conditioning here, I guess. But the point is, your brain is running on about 25 watts. If you put your finger into one of the IBM supercomputers, your finger would melt. It would burn off. The amount of energy that's required to build exascale supercomputers is on the order of the amount of energy to run small cities. So a lot of people say, no, this curve on computing, it's going to stop because of the energy requirements. Well, here we are at Almaden today, and one of the projects was started by Dharmendra Mota. In fact, he stood up on the stage at one point and gave a little 2-minute talk about, there's this new project I want to start at Almaden. It's called cognitive computing. I want to work to build a chip that operates more like the human brain. And his work has progressed. He's made quite a bit of progress. In fact, last year in 2014 on the front page of Science, there was his brain chip, quote unquote, the True North brain chip, was on the cover of Science, and it uses thousands of times less energy than standard chips. And it's a neuromorphic chip, and his goal is to build very, very low energy chips that operate much more like the human brain. In fact, I love this chart, and I love this quote. Each of True North, by the way, that's the name of the chip, True North, and it's the largest chip that IBM has ever had fabbed. It's 5.4 billion transistors. Each of True North's cores is just 1/15 the size of the previous generation and consumes 1/100th as much power. That makes it more than 1,000 times as efficient as chips made with conventional architectures, whereas typical chips suck down 50 to 100 watts per square centimeter of chip space. True North sits just 10 milliwatts for the same area of circuitry. So yes, I believe Moore's Law will continue. I believe we will hit by 2035 one human brain level. I do believe by 2055 we will achieve the full population of chips, and I believe we will have cognitive assistance for all occupations. Now, let's pause for a minute. I showed you my first program that I ever wrote, and in fact, in 1945, IBM played a major role in getting computer science programs started. And there were people who worked at IBM who taught classes at Columbia, where arguably the first computer science department in the world was at Columbia University in 1945. IBMers were teaching some of the courses about digital logic. These were the very, very early days of learning computing and programming and computation. And even in 1970, you know, some 30, 40 years later, it was still relatively primitive. Today, it's quite different. Today, as part of our university program effort worldwide, we make our cloud and Bluemix development environment freely available to all faculty in the world and all students. So any faculty can sign up and get free access to our cloud. And there's this great demo by David Barnes of IBM where in 5 minutes on stage, I'm not going to do it today, but if any of you get a chance to meet people like Russ Beardstall, who's an IBM cloud architect, he can do it. In 5 minutes, they can build an app and deploy it globally in this IBM Cloud Bluemix. And people like Russ, they know how to analyze Twitter. So he does great demos of how to build apps that are based on social analysis of massive amounts of data in Twitter. And this is freely available. So remember me in high school? Writing, key punching my program and waiting a week to get back the printout so I could have the first bug, start working on the first bug. Within 5 minutes, today, you can deploy a global app and start getting users for it worldwide. I couldn't even have imagined that when I was learning programming. But wait, it gets better. Not only do you get access to the cloud development environment in Bluemix, but all of the Watson services, all the cognitive services are freely available as well. What a powerful set of building blocks for computer scientists to build, and others to build things. In fact, that's our goal, is eventually, you know, if you're a zoologist with your cognitive assistant, you should be able to build things that are amazing out of these building blocks. I won't spend a lot of time talking about the Watson platform on Bluemix, but I do want to just say we are entering this new era of computing, and we're empowering makers, not just computer scientists, but all occupations and professions are going to be able to use these new, more powerful building blocks to build amazing things. And kind of to go back to the dedication of this talk to Doug Engelbart, we don't just think of it as artificial intelligence, which a lot of people think of as automation. We think of it as intelligence augmentation, IA. That's Engelbart's vision. Because we want better biochemists, right? We want biochemists who can discover molecules faster to cure cancer. We want zoologists who can come up with better theories of zoology. We want accountants that do better. We want lawyers. I was talking to a lawyer, a Silicon Valley lawyer yesterday. His firm is interested in doing more with cognitive. And he says, what will the lawyer of 2035 be like? What will the lawyer of 2055 be like? How are we going to use this cognitive capability to be a better lawyer, to serve our customers better? By the way, I just should mention that in addition to the True North chip that I told you about, which is really good for pattern recognition and low power, we also have an open power consortium that Samsung, NVIDIA, Google, various other, Apple, various other companies are part of the open power consortium to continue to evolve the chip-level building blocks. But all of this is becoming available on the cloud. So cognition as a service will be available on the cloud, and you'll be able to build these cognitive capabilities into anything. So as you're making your toaster, you can embed cognitive capabilities into your toaster. I don't know what kind of cognitive capabilities you want in your toaster or your refrigerator, but I can imagine cognitive capability you might want in your car, your self-driving car. So let's explore that a little bit more. Because what's happening is this next generation of computer scientists, and really this next generation of students all over, they're getting these very powerful tools, these very powerful building blocks. And what's the most important thing for them to learn? Is it about the if loop? That's what was my first program, by the way, was to use a loop to add numbers together. Now, it was important for me at the time to learn about a loop, and I'm not saying it's not important for people to learn about loops. But what's most important in this era of very powerful tools is that we learn how to work together as people to do bigger and more important things. We need the technologists and the engineers to be able to work with the business people. We need them to be able to work with the social science people for organizational change, because organizations are going to change rapidly. We need them to work with the arts and humanities people because we have to communicate this very complex stuff. So what's really important is that we start teaching, in addition to the fundamentals of computation and computer science, which are amazing and should be very motivating for people to learn, we have to teach our computer scientists to work on teams together with people from all other disciplines to create startups, to create companies that can do some amazing things. So we at IBM, we call this T-shaped people who have depth and breadth across disciplines, industry sectors, and regions and cultures. And our view is that this is a wonderful time to be a computer scientist. I'll just tell you one more story. Before I went to Yale to get my PhD in computer science and start studying how students learn programming, I worked in a startup company that Exxon acquired. It was a speech recognition startup company. This was in 1978 to 1982. And I remember to get the training data, it was really, really hard to get the data that we needed for these systems. Today, my gosh, the amount of data that's freely available on the web, and all the talking on YouTube, what we wouldn't have done to have access to that data. So not only has computing power gotten better, but access to data has gotten better. The building blocks are better. It's available in the API. It's just a whole new world. So let's talk about this whole new world. Because here we are in 2015. What will the world be like in 2035? And by the way, that world in 2035, that's the world where the students of today, the ones who are in university learning computer science, by 2035, they're kind of at the, in the peak of their career, 20 years after graduation. What world will they have helped, what world will you have helped create? And it's an amazing world. Let's talk about that world for just a minute. First of all, transportation. By 2035, no one drives. Cars drive themselves. This is going to have a huge ripple effect on all parts of the economy. First of all, they're going to be much safer. More people have died in traffic accidents on U.S. highways in the last 40 years than have died in all the wars in U.S. history. Cars are going to be much safer. There'll be less people in the hospitals due to injuries from car accidents. There'll be less insurance claims. I have heard there have been, I think, 4 accidents of driverless cars. In all cases, a person driver rammed into the driverless car. So it's going to be much, much safer. If you get a chance, there's a wonderful video not far from here of a blind person. He's a test driver for a driverless car, getting in the driverless car, saying, I want a taco. It takes him to Taco Bell. He gets his taco, and it drives him home. My kids are always telling me, Dad, that means like 8-year-old kids are going to be able to get in the car and say, go somewhere, and the car will take them. And yeah, it's going to be amazing. Water. In California right now, we have a drought. By 2035, no water shortage. 99% of water will be recycled locally. Singapore already does it. By the way, everything I'm showing you already exists today. It's just not well distributed. And most of it was developed at universities. Manufacturing. By 2035, the world that you live in, right now in the U.S., a lot of the stuff we get that's manufactured in the world comes from China. By 2035, it's back local again. Why? because of 3D printers and robotics, primarily robotics. In fact, Foxconn, which makes the iPhones and other stuff, they've created hundreds of thousands, if not millions, of jobs in China in manufacturing. They're aggressively buying robotics. They created those jobs, and now they're going to use robotics. So by 2035, manufacturing looks like a local recycling service. In fact, MIT has designed a car that can be locally recycled, a small local car. Energy. By 2035, no energy shortage. Harvard, MIT, Caltech are working on something called the artificial leaf. You take a thing that looks like a chip, you stick it in sewage water, you shine a light, hydrogen and oxygen come on. Construction. By 2035, buildings are built very rapidly. The Broad Group in China can already build a 30-story building in 15 days. And if you haven't watched the video, watch it. In fact, the chairman of the Broad Group wants to build the tallest building in the world in 5 days. That's his goal for life. And by built in 15 days, the toilets flush, the beds are made. It was a fully functional building in 15 days. And it was more earthquake resistant, higher air purity, better energy efficiency. By 2035, I've already told you about ICT, information communication technology. Our systems are going to have the equivalent power of a human brain. So we'll all have cognitive mediators. In fact, I believe by 2035 we'll be pretty symbiotic with our cognitive assistants. Some might say the cognitive assistant's going to know us better than we know ourselves. It'll certainly have a memory for things that we can't remember about ourselves. Retail by 2035 is social media. Finance is crowdfunding, crowdsource. Healthcare by 2035 is robotic surgery. I don't know if you know anybody waiting for a kidney transplant. By 2035, organs are 3D replicated. And by 2035, education is transformed into cognitive sport. And we learn to work on teams to do bigger and better things. I predict even by 2035, government will work better. I can get into that if we have time. But, so this is just 20 years away. So the students today will be creating this amazing world. And science provides the framework for people to ask and answer questions systematically. Science is going to become increasingly important. And the explanations, science also provides explanations with instructions on how to redo. That's a great thing about science. It's like, not only is it explained, but oh, by the way, if you want to understand it, here's how you can redo the experiment and convince yourself of that. And this is where we kind of circle back to the responsibility part. We're getting this very, very powerful technology. Can somebody drive today without getting a driver's license? No. You don't get access to this powerful technology to drive around and have freedom of mobility until you can drive. So here we are entering this world where we're going to have this incredibly powerful technology. What tests do we need to take before we get the freedom to use it? That's a question you'll have to start asking ourselves. Because this is really powerful technology. Far more powerful than anything in the past. So we'd be very naive to give this technology to everybody unless maybe, shouldn't they understand some of the science behind it? And there's natural systems, cognitive systems, and service systems. Natural systems are understanding and explaining external phenomena. Cognitive systems explain internal phenomena. And service system, this is about people interacting in win-win ways. How do we have a safer, more secure world because people have constructive, valuable things to do together rather than sell drugs on the nearest sidewalk? Right? So these are what we have to understand. We've got a group called the Cognitive Systems Institute group, which is focused on thinking about these cognitive assistants for all occupations. I believe by 2035 we'll all have cognitive mediators with deep knowledge of both the customer, the user, and the provider, the expert, around win-win value co-creation opportunities. It'll be part of what we call smart service systems, where all entities in these global networks will have their cognitive mediator to enhance value co-creation interactions. And this is the Handbook of Service Science, which I co-edited. And what I see happening, you can think of it like a Venn diagram. We're getting more and more powerful cognitive system entities in the world. But inside, there are service system entities. And the difference between a service system and a cognitive system, my dog is a cognitive system, by the way. I love my dog. But my dog has no rights and responsibilities. Young children, elderly people with dementia, they're cognitive systems, but they don't have as many rights and responsibilities as us mature, responsible people, right? So when we get these cognitive, so the way a cognitive system becomes a service system, when it sets up for the rights and responsibilities that go along with being a member of a very productive society. So there's some LinkedIn URLs where we publish a lot of this stuff, and there's other websites you can go to. That's our IBM facility in Italy where I want to work because it looks like the bridge of the Starship Enterprise. And as a kid, I loved the show Star Trek, and so I've got to work at that IBM facility and work on cognitive assistance there. We have a nonprofit professional association where we get together and talk about this stuff and have weekly calls discussing these cognitive assistants. We just had a wonderful call 2 weeks ago from one of the researchers here at Almaden who's developing some wonderful cognitive computing componentry. And thank you very much for listening. I think we may have some time for questions, and I do really encourage people who haven't played with Bluemix to play with Bluemix. Russ Beardsdall is one of our IBM Cloud architects. If he was here, he would give you an amazing demo and presentation. He's done some amazing things with Twitter analysis and really using these powerful tools to build things. But anyway, we can see if there's any questions from folks here. And I do have a little bit more of the talk, but I want to see if there's questions on this first part, if I have time, Don.